Okay, we're gonna go through a solution of the first homework, okay? And the first homework is like this. Okay? And then there's a big block. Okay, which passes through over this part. And on top of that, there is a bar is attached to that, which has no mass. But here we have a mass like that. That's M2. And let me see how I name the display. And the length of the bar is from here to there is B. And this one is I call excuse me, allergy season. And this mass is M1, and we apply force over here, PT. So there are two masses, right? So how many degree freedom this guy has? 2? Gee, you didn't have to come to my office. You already know the solution. So there are two masses, so we need the equations for each of those two masses, okay? Okay? So, excuse me. The first step, we put the inertial reference frame, right? And where we want to put, excuse me, where would you want to put the origin of that inertial reference frame? Anybody anybody has an idea? What?
Left-hand side of the bar.
Left-hand side here? Over here?
Yes.
Why?
Because there is no rotation on the bar, and also it doesn't move, so
Okay.
it's constant.
All right. So what it says is this point is fixed, and so I can put this guy coordinate like that. Okay? That's what you're saying, right? So gotta be careful. If I put this in X and Y, that's fine because this follows the right-hand rule, okay? X, Y, Z. If I put this guy over X, all right? Y has to go up because it's right-hand rule, okay? So that's kind of it's kind of X, Y, Z. Z comes from the blackboard, okay? So Y cannot be down this way. This is awkward. So we have to put Y over here. Now, I could put inertial reference frame here, just away from there, okay? So I will put this guy x prime and y prime and see what happens. And I know you guys, some of you guys start shaking your head as, no. Okay? Now, if this guy is an inertial reference frame, and this is an inertial reference frame, would the two equations that we generate would be same or different?
Slightly different.
What?
Slightly different.
Slightly different. Let's take a poll. How many of you think equations motion generated using this reference frame are different from those you derive using this reference frame? Raise your hands. Why you are so silent? So how many of you think, especially those students out in Changwon, tell me how many of you think you will have a different equations motion if you use the two different coordinate system, reference frame? I don't see any hands. Let me repeat it one more time, because this is trivial but very important, okay? How many of you think you might get a slightly different equation motion if you use the two different inertial reference frame? Did you get it? Did you get my question? Anybody want to make a comment? I cannot hear you. What did you say? Yeah. So, okay, then raise your hands. How many of you think either use this equation or that equation, you would get the same equations motion? 1, 2, 3, 4. Okay. What about those guys who just raising hands just like that? This is what we call half-baked. Yeah, you don't want to eat the bread or food that's only half-baked. So, once again, then you must be agreeing with him. There might be a difference in equations, right? Or no? Or are you confused? You are confused. Okay. The answer is the following. Same equations of motion. Okay? You should not get any difference whatsoever. If in fact this is the inertial reference frame and that is also inertial reference frame, you should get exactly the same equation of motion. Let me tell you why. Let's say distance from here to there is say R. And if I make a position vector from here to there is M1, this is using rho xy. Position vector from the M1 is just R1 is xi. Now, when you use O prime, x prime, y prime, the position vector at M1 is R1 prime is this guy, R plus from here to there, that is xi. Right? just before we worry about anything else, the only difference what we're going to have is the reaction forces is not really, doesn't really depend on the coordinate system. Reaction forces are reaction forces. We are talking about inertial forces, right? So inertial force means here is A1 is x double I. Here is, say, V1 prime is R dot plus x dot I. Okay? If R dot is, say, suppose this guy is moving relative to the other one. Okay? That includes the inertial reference frame, right? So this guy could be a V I plus x dot I. However, A1 prime is V dot I plus x double dot I. By definition, this guy, if it is an inertial reference frame, it cannot accelerate. It cannot accelerate. That's definition of an inertial reference frame. Right? Everybody got it? Therefore, the V dot is 0. So net result is A1 is the same as A1 prime. So inertial force would be exactly the same. Mass times A1 is equal to mass times A1 prime. Are you still confused? No, I want to hear from him. Are you still confused? You are not confused? This is very, very important. Okay? Everybody got it? Is it clear now?
But if there is a x term in equation of motion, then it's two different equation of motion.
What is it?
If there is x term in equation of motion,
If there's an x term,
yeah,
there's no other term where the position vector would make a difference. The only place where the position vector would make a difference is in the acceleration. Okay? The reaction forces would not be dependent on the position vectors. Okay? All right? Now, let's say to make everybody happy, let's write it M2. So we need the acceleration at M2 too, right? So the position vector of, say, M2, right? If I use OXY system, say R2 is R1, because this guy goes this way, and then go down to center, the mass center over here. So R2 plus, if I say this is B, say unit vector along this line is, say, E, and then the vector length is EB, PE, like this. So this is PE. But this is I, this is J, E goes like this. Okay? So this is minus I, so to speak. So that unit vector along this line, E, okay? So E is what? This is theta, this is theta. So that's what? Cosine theta J, but it's negative of that. And this one is, the length was here is, this goes like that. And that one like that. And that one is, this is where the theta is. And that is minus sine theta I. Okay? So this guy, E, we can replace guy. Let me see. Oh, because of this guy going that way, that's a plus. Okay. Minus, minus, that's a plus. So this one is a sine theta I plus cosine theta, minus, I'm sorry, cosine theta J. Now, O prime, X prime, Y prime is R2 prime is nothing but you just keep adding this guy. R plus R2. Right? So R2 double dot, which is A2, has to be equal R2 prime double dot, which I call A2 prime. Okay? So for the mass 2, the acceleration is the same, whether you compute it acceleration based on this frame or this frame. Okay? Everybody happy now? All right? Okay. Now, then what we need now is to compute, identify some reaction forces. And to do that, we need a free body diagram, right? So we have a 2 free body diagram, okay? So there's a 1, that's mass 1. There's another one, that's mass 2, okay? So in the mass 1, first of all, we start with something very easy to identify. This guy has a weight because it's on the gravity field, right? So the weight is downward, that's mg, and minus j, because j is this way, and I is that way, the unit vector, okay? Got that. There's applied force, Pi. Okay? Since I take this guy out, there is a reaction force. Because this guy, this rail is the one supporting this weight, right? So there will be a reaction force over here. Which, since I don't know, I will just use it, NJ. Okay? Now, on top of that, there's this rod that's pulling it down, this mass. And there's balance between that. And that would be, there's an angle theta. And you can do any way you want. I can put is plus or minus. Okay? And if I do that, that will be n minus e, because my e is this way. Since I'm showing this to be, this is arbitrary. I can do it this way. It's okay. All right? Any. Then we have one thing. Normally when you push this guy through, there will be some friction, right? Right? So let's just think about it. Now if I put my razor, I'm gonna push this way, okay? All right? Which direction this guy will experience friction force? Which way? Yeah. So I'm assuming this x is on a positive direction. In that case, I will have a friction force that's proportional to friction by definition mu n. But since this guy can be up and down, what I do here is I use the sign x. Let me write that down pretty clearly. So mu n as a friction force times, in other words, when I assume this one is moving this way, I will have a friction force heading that way. So it depends on the sign of x. Okay? Anything else? There's one thing still critical, one thing still missing on this free body diagram. My definition of free body diagram is different from what you learn. I include every force, including inertial force. Okay? What you learned from your undergraduate was sum of the forces equal to mass times acceleration. That's what you learned, right? Now, that's not what I'm doing here. And this guy is really plus F inertia. Like that. Okay? So here, what I'm going to do here is, assuming acceleration is this way, my inertia will heading this way. That way. Okay? So now all you have to do is just sum this guy vectorially, x components and y components. All right? And you have equations of motion. Okay? For mass 1. For mass 2, okay? The first thing what we know here is, at this point, there's a Newton's third law, action and reaction. This guy will act here this way. So that this one will cancel this one. This is Newton's third law, action and reaction. Hey, suppose if I sit down on this chair like this, I feel pressure. But this chair also will have a pressure. That's equal and opposite. Okay? So this opposite is just NE. That I know. Then I have this guy. Right? Anything else? I think that's all. That's the only thing I have. I forgot. There's a gravitational force. Okay? And then I don't know which way this guy will go. I'll just put something like that. Minus M2, A2, or A2 prime. Doesn't matter. Since they are same. So, how many equations we get? We get x, y, we get one equation, right? Here, we get two equations. Excuse me. So we get two equations here. Here's x and y, right? So we have four equations. We only need x and theta are the two unknown kinematic variables. Why are we having four equations? What do you think? Huh? Why are we having four equations instead of two equations? There are two, right? Okay. I noticed that very few of you are writing down the today's lecture. That's not a good habit. It's not a good study habit, by the way. Even if when you know it, it really pays for you to write it down, what's written on the blackboard. Believe me. If your primary school teacher didn't tell you, I'm telling you in graduate school. Okay? It's very important. What you see doesn't really register until you move your fingers. Okay? This is a very well proven educational research. When you see, when you write it down, you register here. When you see it, you don't experience. It goes away. Just like when you see a movie. Okay? And I notice very few of you are writing down. Okay? It's very important you write it down. It's a very good study habit, actually. By the way, when you write it down, you can also tell that in the next class, oh, Professor Casey Park, you made an error on your lecture yesterday, the other day. You can give me a hard time too. Okay? So the reason why we have 4 equations will become clearer if I say n is x component I plus y component j. N actually consists of these xy components. Okay? So now suddenly we have 4 unknowns. Okay? So instead of doing this, I could have easily said xi plus yj, and here, okay, minus xi plus yj. You know how to sum the forces, right? That, at least I don't have to do that, right? So you will have 2 equations and 2 equations. Okay? It's very important you use a vectorial concept. Okay? There's one more thing. Okay, here's it. I take it back. This one was, I wrote it like minus NE. Because x and y are not independent. They are determined by this angle. Okay? So this guy is like that. There's one more equation. All right? So I have one more unknown. I use 2 n's. That's why I got really confused. I use n over here. Let me just use something else, okay? I use the p. I'm running out of sign. Let me use a t, because it's really tension over here. So I have a t. So I have 4 unknowns. X, theta, n, which is the reaction force on this mass one. T is the tension of this rod over here. Okay? So I have 4 unknowns and 4 equations. Wow. I was hoping to use only 20 minutes. I overspent my time. Any additional question? For those out there in Changwon, do you have any question about the homework solution? Is it clear? Thank you. These are very elementary that you should have learned if you took any mechanics class in your undergraduate years. So we are just going through that. But I want to make sure that I'm with you before I rush into things. Okay? Now, let me see whether I should go over the solution Thursday instead of today, today's homework. So I think I will stop here as far as homework solution goes. And I will go over the lectures first. Okay? So, let me stop here, and then we will go over the homework, second homework solution very briefly Thursday. Let me just emphasize one more time. It's very, very important, the coordinate system you put it in, okay, is let me make sure, an inertial reference frame. Then it doesn't really matter whether you put the origin over here or in your bedroom, okay, or somewhere in the top of the building. It really doesn't matter. You are going to have exactly the same equations motion. But it better be an inertial reference frame. If it's not an inertial reference frame, your equations of motion may or may not be correct. Okay? It's very important. All right. So your question was, will I get a x-dependent forces and moments? The answer is no, in this case. Okay? All right, let's continue on rigid body motions that we started last week. So for a rigid body, going through rotational motion and translation, here we've attached the two reference frames. One is this guy's inertial, and we attached here another frame. Okay, I think I used the sign convention like this. This is capital X, capital Y, and capital G, and this is XYZ. And this is a big O. This is a little o. This XYG is an inertial reference frame. This XYZ is it's not an inertial reference frame. Why? This guy is not, I said. So what I call body fixed. Why a body fixed frame usually is not an inertial reference frame? Anybody want to articulate? Including those at Changwon?
Because body can
Yeah. The body fixed coordinate can undergo acceleration and O, rotation. The inertial reference frame V has to be constant. And no rotation. Okay? Of course, Galileo didn't mention this way in modern terminology, but it's really due to Galileo. Okay? Somewhere around 1612. Okay? So we call inertial reference frames, the concept of social inertial reference frame is, we call, it's coming from the Galileo's principle of relativity. Okay? So it's clear that this guy can go through rotation for sure, right? The minute it goes to rotation, this frame cannot be inertial reference frame. Okay? So you can write equations of motion on that, but it's really projected back into inertial reference frame, and then you can write equations of motion. Okay? In any case, we had two equations of motion. Okay? One, translational equation of motion, right? So the translational equation of motion was something like this. M A0, right? Plus cross RC plus omega cross RC equal to all the applied force. The other one was the rotational equations of motion is J omega dot plus skew symmetric matrix J omega. Okay? And on top of that, let me see, plus MRC cross, I call it just A, okay, and A equal to apply the moment at O. So that's what we wrote. We derived. Now, since angular orientation in rotational motion plays a very, very important role, we're going to talk about angular orientation. So this whole thing, what makes the rotational equation of motion complicated is angular orientation is really kind of difficult, or you might say cumbersome, to compute. The reason is in translation equation, say R which is a position vector, is simply xi plus yj plus, gk, something like that. In other words, they are vector. Okay? In angular orientation, we don't have, say, suppose this is vector, or rotational vector. We do not have this. There's no such thing. In other words, angles cannot be represented in terms of vectors. They are not. Okay? And that's where the difficulty comes in. When you set and down everything else, this is where the problem is. And that's what makes solving rotational equation motion difficult. Okay? So, what we do, today we're going to use good old Euler angles and Euler parameters. In other words, we need to learn how to represent angular orientation. Okay? So, angular orientation. So, angular orientation needs two things. One, axis of rotation. That's a vector. Two, rotational mount. Usually some kind of angle. Okay? All right? So let's take the simple example. So that's XYZ. Suppose if I rotate the g-axis by theta g amount, this guy will go through that part. This will go around that part. Suppose this guy was unit vector. This k. This is I. This is j. And then this becomes, say, I. We designate this guy I prime, j prime. Okay? All right? So you all know from your undergraduate, this is I and j, this I prime, j prime, so that I prime and j prime is given by after this much rotation, we have a cosine, sine, minus sine, cosine, where C means cosine theta g, S means sine theta g. You've seen this so many places, right? You know how to do that. Okay? So, this is probably what you learn. So let's say, in this case, K was an axis rotation. So this guy just rotated, but it didn't change it. It didn't go to angular change. So K prime is K. So I prime, J prime, K prime. You write this way. I, J, K. So this is CG minus SG 0. Minus SG CG 0, 0, 0, 1. because 1 means K prime is K. Okay? So this is probably then, first we rotate K. Next what we do here is we rotate this guy, okay? I prime. So that's theta x, okay? Or I could use theta 1. Then this guy will move. And finally this K will rotate this way. Okay? So please remember when K is axis rotation, that's 1 and 0, rows and columns 0, right? And then there's the cosine, sine, minus sine, cosine. So we can use this one by switching this guy. Okay? So the K becomes, in this case, this guy is I double prime. So I becomes J double prime. Let me see, Ki, J becomes K. It's like that. And 1, 0, 0. Okay? And 0, 0. And I have here J prime, K prime, I prime. Okay? Then I have cosine x minus sine x, plus, I'm sorry, minus sine x, cosine x. It's like that. Now after you make a 3 and 1, you go back and redo it again at 3. That is, you rotate this guy. And that's J, K, and I double prime. That's 1. Okay? And we are, since K, yeah, that's true. And then I have C1 prime. S1 prime minus S1 prime and C1 prime. So this one, I can rewrite this one, I double prime, J double prime, K double prime. Okay, remember here I am rotating I. So 1, 0, 0, 0, 0. So I make a subsequent rearrangement this guy. So J, so J double prime was a C J prime S K prime. So C J prime and S, this is X, like that. K double prime is minus SXJ, minus SX, and CX. And this guy can be written I double prime, triple prime, J triple prime, K triple prime. When you guys in primary school or junior high or senior high, have you ever heard thing called Akiba method? Never heard of it? Ask your nephews and nieces or your younger brother. The Akiba prefecture in Japan, year in, year after, when they do the academic status test, they rank the first in Japan. And you know why? They require students write it down, and then teachers go over your notes. That's the only thing they do. And their student excels in the academic performance. So anyway, so this is ijk's I double prime, j prime, k double prime. So here, that was a 1, 0, 0, 0, 0. So j is a cosine. I think a sine here. 1 prime, 1 prime. And then minus S1 prime, C1 prime. So this guy then, I will call this guy R, okay, theta 1 prime, okay, and this guy is R triple prime of this guy is where's the K? Let me see, where's the K? Oh, but this guy can be written this one. So this is that's R3, I'm sorry. 1, 3, 1, 3. So this should have been 3. I don't know why I have 1. So this is a mistake. This one was 1. That was a 3, and then 1, and 3. So it should have gone that way. This is C1, S1 prime, and C1 minus S1 prime. Okay. So this I will call R theta X. Sorry. So 1, 0, 0, 0, 0, K, C, S, 1, 1, 1, minus S1 prime, C1 prime, like that. So that's 3 prime, and which was followed by theta 1 and R theta 3. And then that will be ijk. So this is all theta 3 prime. And this one is all, that's all theta 3 prime. And this one is all theta 1. And that one is all theta 3. So you go through this one gives you prime, when you go through this, that two successive rotation, that gives you this. And then when you go through one more time, this one will give you that. So you go through three successive rotation. Now, it's not unique. What I did here is what we call 3-1-3 rotation. Okay? I can do 1-2-3 rotation. I can do 3-2-3 rotation. And the angle that you have, they are not determined uniquely because of this. So you have an initial orientation, you have a final orientation. You can decompose in many different combinations. And this is where the number 2 trouble comes from in describing the rotational motions. Okay? So there are many different representations. So in order to overcome, we're going to continue this, right? Yeah. You're going to take time off? Well, you have a question? This one? This one? 이거요. If you want, you can just get rid of it, okay? I just made it up something. I just want to distinguish this cosines and sines from this. Okay? So, this one? This one means cosine theta 3 prime. Okay, I haven't finished it here, this guy. This guy is, first we rotated K, right? Next we rotate I, right? We're going to rotate this one. So you can use this guy as a theta 1, this guy is a theta 3, and this guy is a theta 3 prime. Okay? Yeah. I was making it up as I was going through. Okay? So I just use a prime instead of something else. Because this is theta 3 prime is rotating around this axis, not that axis. This is what we call 3-1-3 rotation. Don't ask me. This is some people already invented this. I'm not inventing this one, okay? I'm just telling you there's a such rotation. And you could use 1-3. You could use 3-2-3. In fact, one of these will be a homework assignment this coming Thursday. Okay? Now, so this is cumbersome. This is what undergraduate days you do. But we gotta know this, okay? You have a question?
Is the order is important?
Order? Order is important when you wanna resolve, say, angle, orientation moved after certain time. This guy went through this way. And the difference is, I can call this guy as some R, IJK. How you dissolve this guy, you give yourself a rule. I'm going to use a 1-3 rotation. Then you have a formula. I'm going to use a 3-1-3 rotation. You have different formula. That's all. Okay?
I mean, 3-1-3 is equal to 3-3-1.
Yeah, but the angle would not be same. The amount of angle depends on what sequence of rotation you went through. Okay? Yeah. So, this looks like an awful. So let's now, this is what I did. The reason I went through very quickly is this is what you would do in undergraduate. We're not going to do this in graduate course. We're going to do something, rotation representation, that is independent of rotational sequence. You like that? Huh? You like that better? Because we're going to have this R matrix, which is independent of different rotational sequence. You will like that, right? And that's why we are in grad school. Let's do that, okay? All right. So what we're going to do the following. Remember, here is, we need axis rotation, 2 amount of rotation. Okay? So what we're going to do, we're going to represent we call that, this is vector, so I call that n, and I call that just the theta. We're going to derive this rotational matrix, 3x3 matrix, using only axis rotation and amount of rotation. Okay? So, what I'm going to do here is, I have a vector, small, okay? And I'm going to rotate this guy along this unit vector over here. Unit vector is heading this way. I'm going to rotate this guy some amount. Maybe this amount. Maybe this amount. Okay? So this guy will go through rotation about that way. Okay? Let me just get rid of this guy so that you will not be confused. Okay? So after rotation of that amount, which is theta, my new vector is here, which I will call R prime. Okay? So this is O. Let me say this is P. P goes to P prime. P prime. All right? And I put this guy O in such that if I look at this triangle over here, that triangle this is a triangle COP. So this is O, this is P, this is C. That's a right angle. So that one is R. There is a vector over here, unit vector is N. So I rotated this P like this by angle theta. Okay? So this amount, you know from your vectorial thing, the distance from here to there is R dot N. Right? This distance from here to there. You dot with this guy with this hand, that's this distance. Right? Okay? And when I write down as a vector, then that direction is N, so this is a vectorial distance from here to there, along this line. Okay? Now I'm gonna extend this guy as a say circle. And I write it down here, big circle. And that was O. That's a P. And that's P prime. Okay? It's like that. So here, what I say here is my vector from P to O, PO as a vector, is this one minus that one. So R, PO is this one plus that one is this one. So PO is minus R is my PO. So from here to there, it's got this, okay? And from the vertical from here coming out here, I have N vector. So if I really wanted to write this guy, this is coming out of a blackboard. This is my N vector. Okay? So now let me just draw this guy. There is a normal vector from here to there. Okay? Which I will call Q. This is a perpendicular. Then this is my N. It's complicated, isn't it? So if I take a N cross a P, I will have a OQ. N cross P. Right? Look, I cross J is a K. K cross I is J. So if I take this N and I the OP, not PO, OP. In other words, N cross OP will have OQ. Okay? Because this is unit vector, this gets the magnitude and the direction. It's like that. Then I'll have OQ. So now, let's look at this point. This point can be resolved this way. From O to here, okay? Which I will call R and P prime. So my R prime is here is from C to O, which is this guy, okay? CO. So I came from here to there. Then I have O to P. That's my R prime after rotation. I know this guy. This guy is nothing but R, and then OP is OR plus RP prime. Okay? So this angle is a theta. So the magnitude of this guy and this guy are all same. They are on the circle. Okay? You know, the magnitude of OP is the same of OP prime. Same as OQ. Okay? They're all same. So the OR is this guy is OP times the distance is a cosine theta. So this times cosine theta is at that magnitude. But the direction has to be that direction. So this is OP cosine theta is this guy. And RP is this guy is this distance OQ. Okay? And sine theta. Okay? Now, OQ from here to there, we already computed this one. N cross OP. We now realize OP is just a negative over PO, right? If you measure a vector this way, if you measure the other way, it's just a negative, right? Okay, that is just R minus NR, and so that we got OQ. We replace this guy by N cross OP. And we know what the OP is. OP is this guy. So then what I have here is NR, N plus. OP is this guy. Okay, and there's a cosine theta. Okay, and this is OP is that one, and that one is plus R minus NR, and then this is a cross plus N cross and sine theta. Okay, so finally writing it down here is, if you will work that out, it comes out to be very simply just like that. That R cosine theta plus 1 minus cosine theta AN N plus N cross R, not A, R, I'm sorry, sine theta. That we can write in the following way. Identity dyadic cosine theta plus 1 minus cosine theta, okay, N dyadic plus N sine theta and dyadic, not dyadic R. We can write it this way. Now, what is the meaning of N? N has a, it's a unit vector, but unit vector has also magnitude of and also direction. Like that. So we have a unit vector and amount of rotation. We can write it this way. And that is symbolically we can write R, axis rotation, amount of rotation, gives you rotated vector. Okay. We got, how much time do we have? We got like, we started 40. So let me have 5 more minutes, okay? Is it okay? I think I have only 2 more minutes. So let me have 5 more minutes, especially for those. Okay, so let me erase all this, show where the application of this guy is. In other words, you have a question? You have a question? Okay. If this guy is really claimed to be the rotation matrix 3 by 3, we should be able to reproduce the Euler rotations that we just went through, right? Right? So remember what we do is IJK. We made a K rotation. So N is a K in this example. Amount of rotation theta is theta G. Like this. Okay? So we're going to apply this guy to this. Okay? And we're just going to look at this guy. This guy. Okay? So what we're going to do here is the R could be IJK in this case, right? R could be IJK. So here, we just going to pretend this prime is R cosine theta, this vector. I'm not going to say anything what is R, okay? So R is some vector. So R could be R1 I plus R2, R2 J plus R3 K, okay? So that R. Now here's a 1 minus cosine, R cross N, here K, N is K. So R dot K, R dot N is R dot K, because K is the axial rotation. Okay? So when you do dot product, you only have R3, right? So this guy is R3. And you have N, this guy, plus, now we're going to do the cross. Cross means is K cross R1I plus R2J plus R3K. When you cross, that disappears, K cross IJ, so R1J. K cross J is minus I, R2I. Here is, this guy is R1J plus, minus R2I. Okay? And this guy, I can just rewrite the whole thing is R1I plus R2J plus R3K. So I'm going to write this guy, okay? That one I can write R1 prime, R1 prime I plus R2 prime J plus R3 prime K, okay? Or the other way around. So that means I, J, K. So let's collect all the items. Items here is R1 cosine theta. There's no R1, but there's a N means K here. There's no I. Then there's a R2, I forgot sine theta. There's a sine theta, okay? So there's a minus R2 sine theta, okay? J, there's this J, okay? R2 cosine theta. There's no J, there's a plus R1 sine theta. K, I have cosine theta R3. Here's, R3. Plus 1 minus cosine theta R3. And nothing else. So by taking I, J, K identity, so R1 prime is R2 prime, R3 prime. You can write it here. Here is it I, J, K. And here R1, R2, R3. Here I have here is cosine theta minus sine theta, 0. This one is cosine theta, and sine theta, 0. This guy is this one and that one cancels. You only have 1, like that. Now, it looks different from what we did. What we did was I prime, J prime, K prime was the following. Cosine theta, sine theta, minus sine theta, cosine theta, 0, 0, 0, 0, 1. I, J, K. Okay? But here it's just the signs are reversed the other way around. The reason is this R1 prime, R2 prime, Rj prime put back on IJK frame. Okay? Not J prime, K prime frame. Okay? So these guys are all IJK, and this guy is all IJK. Okay? So in order for this guy to be, if you want to put this guy to be I prime, J prime, K prime, in other words, a prime, 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 it's just the other way around, like that. So this one put back into the original unit vectors, not the rotated unit vectors. Okay? That's the only physical interpretation you have to do. Now, if you don't like this, all you have to do, very easy, change this plus to minus sign. Everything will turn out to be like this. Okay? Because this guy, the minus one, is nothing but projecting wrote onto this is what we call in theory, in higher math, called push forward operation, minus n cross I. Plus n cross r means push backward. You rotate it, but you are going back to there. Okay? So, take my word for it. All you have to do is change this plus to minus sign, and you will have this familiar rotation. So this one is good for any problem. So the only thing you need to know is axis rotation and amount of rotation instead of going through 3 rotations. Okay? You have one rotational angle and axis rotation. You have a rotational orientation matrix. Okay? And that's all I'm going to quit today. Thursday, there's better ones. We can express this kind of very nice parameter, not angle, some parameter. And then we can actually integrate those equations very easily. Okay? But I sketched that out, and the only thing I want to do on Thursday is use rotational equations to compute what we call stability. How cars overturn, okay? Ships get overturned. That's very important. We call stability. If the vehicles are not stable, it really doesn't matter, right? So we're gonna conclude this rigid body dynamics section by studying using the rotational equations to study stability of a moving vehicle, be it automobile or ship, train, doesn't matter, airplane, they all and satellite too. Okay, we can study those using our simple rotational equations motion. Okay, so that's all there is to it, and have fun with the homework. The current homework is very simple to derive. Remember the recipe I described. What do you have to do first? Huh? Yeah. Your choice of inertial reference frame. That's how you start. Second, position vector. And accelerations, right? Okay?